Welcome to the worksheet for section 9.5. We will continue with counting. So first some notation. N choose R is the number of R combinations out of an element. So that means the number of subsets of size R of a set containing n elements. And N choose R, we have a formula that's n factorial divided by r factorial divided by n minus r factorial. And we will also look on counting permutations of a set with repeated elements through an example. So this video will contain problems 1 through 3. So let us start with problem 1. List all two combinations of the set ABC and compare with the value of G3, choose 2. So two combinations are subsets containing two elements. So there are AB, AC, BC, and there are 3 of them. And when we check, n choose 3 is 3 factorial by a formula divided by 2 factorial divided by 3 minus 2 factorial. 3 minus 2 factorial in the denominator is 1. And 3 factorial is 3 times 2 factorial divided by 2 factorial is 3. So it agrees with our list. For the second problem, we will consider counting bit strings of 0 ones of length 16. So first, how many bit strings of length 16 contain exactly 7 ones? Then how many bit strings of length 16 contain at least 1 1? And finally, how many bit strings of length 16 contain at most 1 1? So for part A, to count how many bit strings have exactly 7 1, we choose the positions for the 7 ones. Once those positions are chosen, the rest of the digits are zeros. So out of 16 positions to choose 7, we have 16 choose 7 choices, and we can leave the answer as this number 16 choose 7. We don't need to simplify. Part B, how many bit strings of length 16 contain at least 1 1? So we will use the difference rule. Bit string containing at least 1 1 are all the bit strings minus the bit strings containing no 1. And notice that there is only one bit string containing no digit 1. That's the all 0 bit string. So we get 2 to the 16 minus 1. And finally, part C, how many bit string containing at most 1 1? We will divide into two cases: bit string containing exactly 1 1 and bit string containing no 1. The bit string containing exactly 1 1, we need to choose the 1 position out of 16 for the single one. There are 16 choose 1 choices. Bit string containing no 1, that's 1, all 0 bit string. So 16 choose 1 when we evaluate is 16 plus 1 is 17. So 17 is the answer for part C. And finally, the third problem, we will look on Morse code. Symbols in the Morse code are represented by variable length sequences of dots and dashes. For example, A is dot dash, I is dot dash 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 dash, and so on. Actually, it's interesting, this code, because of its simplicity, is still used by planes and boats in case of emergencies, in case all other radio contact fails. So how many different symbols for this problem can be represented by sequences of 6 or fewer dots and dashes? Again, we will divide to sub-problems, because we know how to count strings with fixed number of symbols in them, not variable. So A sub I will be number of sequences of dots and dashes with exactly I dots and I dashes or dashes, so exact length I. And A1 is 2, either dot or dash. A2 is 2 squared, because in the first slot of the string, we can have two options, dot and dash. In the second slot also two options. So AI by similar argument is 2 to the I. So the number of symbol, number of sequences of length 6 or fewer of dots and dashes is A1 plus A2 plus A3 plus A4 A5 A6, and so we see that's 2 to plus 2 squared plus 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, and again it's okay to leave the answer this way. We don't need to fully evaluate. So that's the answer for part 3. So we stop this video here. Thank you.